Hello, I'm Jack. Welcome to Practical Programming channel. In this video series, you will learn everything you need to get started with WebGPU Graphics Programming. In the last several videos, I explained how to create some 3D primitives and 3D wireframes. However, when renders this graphic object with solid colors, you may find that the image looks flat and is failed to illustrate the 3D nature of the object. This is because we neglect the interaction between light and surfaces in our objects. Lighting is one of the most important factors for creating real-world 3D graphics objects. However, WebGPU does not have much built-in features on lighting. It just runs two functions, vertex and fragment shaders. If you want the lighting effect in your 3D objects, you have to create a lighting model yourself. In this video, I will show you how to build a simple lighting model in WebGPU and how to use it to simulate the light source. Here we will discuss three types of light sources: ambient light, diffuse light, and specular light. The ambient light is the light that illuminates all objects uniformly, regardless of their location or orientation. It is a global illumination in an environment. The diffuse light and specular light reflection depends on the angle of the light to the surface. When the light hits the surface, the diffuse reflection occurs all the directions, while the specular reflection occurs only a single direction here. So you can see the difference between the diffuse and specular lights. Here shows the light reflection on the torus surface. On the left is the light effect from ambient light source. At the center shows the light effect from both ambient and diffuse light source. On the right is the light effect from ambient plus diffuse plus specular light source. You can see that the torus with only the ambient light looks flat and no 3D features. The torus with the diffuse light has the 3D effect. You can see the 3D nature, while torus with the specular light looks more 3D and realistic. The light reflection depends on the angle at which the light hits the surface. The angle is very important to the diffuse light and the specular light. This angle is always associated with the surface normal that is perpendicular to the face. To build a light model, we need to calculate the surface normal based on the direction in which the surface is facing. Since the surface of a 3D object can be curved, it can face different directions at different vertices. So a normal vector is different for different vertices. That is, a normal vector is always associated with a particular point on the surface. Here I will show you how to calculate the surface normal for some simple 3D shapes, including the cube, sphere, cylinder, and a general quadrilateral surface. For a cube, it is very easy to calculate the surface normals. For example, the front face is pointing towards the screen, so its normal is 0, 0, 1. The right face is facing direction to the right, so its normal is 1, 0, 0. The top surface is pointing toward the top, so its normal is 0, 1, 0. Similarly, we can easily specify the normals for the back, left, and bottom faces. Note that the length of the normal vector should always be 1. That is, we need to normalize the normal vector. The normal vector for a unit sphere is simply x, y, and z. That is, the normal vector is identical to its vertex positions on the surface. In the spheric coordinate system, it can be written in this form: sine theta cosine theta is x component, y component cosine theta, z component is minus sine theta sine phi. For a cylinder, we can divide this surface into three parts: top face, bottom face, and a round tube. The normals for the top and bottom face is very simple. For the top is 0, 1, 0, and for the bottom is 0, minus 1, 0. For the round tube, its normal can be written in this form: the x direction cosine theta, 0, this means independent, the y position. The z is minus sine theta. It's just this coordinate in cylindric coordinate system. For a general quadrilateral ABCD, its four vertices may not in the same plane. We can divide it into two triangles ABC and CDA. We can calculate its surface normals in two steps. First, we calculate the weighted normal for each triangle, which is weighted by the area of that triangle. The triangle with a large area will get more weight. As we know, the area of the triangle is proportional to its cross product of these two sides. For example, for the triangle ABC, we have this, the weighted normal BC this side and CA this side is cross products. It gives the weight and also gives the direction. This is cross product for the triangle CDA. So we first calculate the weighted normal for each triangle. The next step is to calculate the surface normal from weighted triangle normals. So surface normal is equal sum of these two weighted normals of the triangles, and then we normalize it. Here is the formula. So surface normal equal to normalization of these two cross products for these two triangles. Then we can merge the similar terms and get final results. Normalize cross products CA and DB, CA and DB. Just a cross diagonal, DB and CA. So this is surface normal for the quadrilateral. We will use this formula to calculate the light model for 3D surfaces. Once we have calculated the normal vector at a vertex, we can use it and the direction of the light to compute a light intensity. For diffuse light, its intensity is proportional to the cosine between light vector and the normal vector, just like this. This is N normal vector. This is L, this is light direction. This intensity proportional to the cosine alpha, this angle. Assume ID is diffusion intensity, KD is diffusing material property. So the ID, the diffusion intensity, can be write in this form: KD times maxima cosine alpha and 0. The maxima and 0 here is try to avoid negative value. We can also add the ambient light to the diffuse light intensity like this. So here is IA is the ambient intensity. So just put this number here, because IA here is independent angle. So just give a constant. For the specular light, we have two models. One is a fan model. This model is very simple. IS is specular intensity, KS is specular material property, S is sandinesss or roughness of the surface. So the fan model gives this formula: IS equal to KS times V dot R and S power. V is view direction, R is reflection direction. One issue with the form model is that the angle between the view direction and the reflection direction has to be less than 90 degrees in order for the specular form term to contribute, because they have S squared. This V dot R must be positive. So this requires the angle must be less than 90 degrees. In order to overcome this difficulty, we can use the Blinn form model to address this issue. Blinn form model here has a different set of vectors for its computation based on the half-angle vector. The half-angle vector is defined by light direction plus view direction and normalize it. So here is light direction, this is view direction. Here is H equal to L plus V. Then this Blinn form model is given by this formula. V dot R replaced by N, the normal vector, dot H, the half-angle vector. Here, the angle between N and H is always less than 90 degrees, so this avoids the difficulty by the form model. Okay, let's go to the programming part. Okay, we will use the git tool to clone the source code used in the last video. Here is the download link at GitHub repository. From this link, you can download the source code used in the last video. Now open a command prompt window and run the following command: git clone, and paste this link. This will generate a WebGPU 16 folder on your local machine. This folder contains all the source code used in the last video. Now we want to change the name of WebGPU 16 folder to GPU 17. Rename U17 and cd into it. At this point, we are going to start Visual Studio Code with the command code period. This is Visual Studio Code interface. Okay, we can close this welcome page. Now here contains all the source code used in the last video. Now let's implement the light model in the Cedar code. From SRC folder, open the cedars.ts file. Now we need to replace its content with new code. Here we first define an interface called light inputs. Here contains parameters used in the light computation. Here the cedars function takes light inputs interface as its input argument. Inside this function, we first define the default values for the input parameters. Inside vertex cedar, we first define a uniform structure that contains view projection matrix, model matrix, and a normal matrix. Here, the normal matrix is a transformation matrix for the normal vector data. When applying a transform to a surface, we need to derive normal vectors for the resulting surface from original normal vectors. If we make a non-uniform scaling transform to the surface, the transform to the normal vector needs a special consideration. In order to transform the normal vector correctly, we don't simply multiply them by the same matrix used to transform our object, but we need to multiply them by the transpose of the inverse of that matrix. Since WGSL does not implement the matrix inverse function yet, so we have to make this transpose of the inverse of the transform matrix in TypeScript and then pass it as a uniform matrix as shown here. We then define the output structure. Here contains 3 variables. First, the built-in position, another one is V position, and V normal. There are 2 input parameters for the vertex main function. One is the vertex position, and the other one is the normal vector data. Inside this main function, we only perform model transform on the V position because it is used in the light calculation. The V normal is the result of normal vector data multiplied by the normal transformation matrix, and the default position is obtained by performing model, view, and projection transformation on the vertex position data. For the fragment seeder, we first introduce a uniform structure that contains 2 variables. One is light position, and the other one is eye position or view direction. The main function takes V position and V normal from the vertex seeder as its input argument. Inside this main function, we calculate the light model. For the specular light, we implement 2 models, that is, fun and blind fun models, which are specified by the is fun parameters. If it is equal to 1, the fun model will be used. Otherwise, if it is equal to 0, the blind fun model will be used. The output color from the fragment seeder will be weighted by the light intensity. You can see from the ambient, diffuse, and the specular light sources. Okay, this is the seeder we will use for calculating the light model. Now we can save this file and close it. Next, in the SRC folder, we will add a common TypeScript file called light.ts file. Add a new file, light.ts file. And we will add some code to this file. You can see here has some error. This is because we didn't install the npm packages for this example because we don't need it. Here, in addition to the common function from the help.ts file, we also introduce the seeders and the light input interface from the seeders.ts file. This file contains a new function called create shape with light. This has 4 input parameters, including vertex data, normal data, light inputs, and the is animation parameters. Next, we create a vertex buffer using vertex data and a normal buffer with normal data. For the render pipeline, here we have a buffer attributes. This is an array. The first element with the seeder location 0 represents the vertex data, and the second element with seeder location 1 represents a normal vector data. The other part of the pipeline is the same to that we used before in creating a 3D cube. Next, we create a uniform data, including normal matrix, model matrix, view matrix, and view projection matrix. For simplicity, here we set light position equal to eye position. That is, light direction is the same as a view direction. We then create 2 sets of uniform buffer. One is vertex uniform buffer, and the other one is fragment uniform buffer. The former is used to store model matrix, a view projection matrix, and a normal matrix, while the fragment uniform buffer is used to store the eye position and the light position, which will be used in calculating light model in the fragment seeder. Inside this draw function, we write model matrix and normal matrix data to the vertex uniform buffer because we need to use the real-time model matrix to perform various transformations, not how we construct the normal matrix. First, we invert the model matrix to get the normal matrix, and then we transpose this normal matrix and get the final normal matrix. Here, we also need to use the correct offset to write the model data and the normal data. Here we use 64 and 128, this offset, because each matrix is 4 by 4, so the offset is 64. Finally, we set the vertex buffer and the normal buffer to the render path, and also set a uniform binding group to the render path. Okay, we completed the programming for calculate light model, so we can save this file. I have created a GitHub repository to host the source code used in this video. I will post the link for the source code below this video. You can click the link to download the source code. I will end this video here. In next video, I will show you how to build a 3D cube with lighting effect. See you next time. Bye.